I'm here today. I'm going to talk to you about boosting your game's performance with Unity 6 profiling tools. If you're looking for anything else, you're in the wrong place, but you've probably seen that already. My name is Peter Hall. I've worked in the games industry for 20, 25 years, something like that. And optimizing games is one of my favorite things to do, especially as part of my job. It's so satisfying when you actually do some optimization work and you get to a game that's running smoothly and see people sat down playing it. It's an amazing thing. Hopefully, with some of the tips and tricks I've got here today, you'll all know what that feels like as well if you don't already. I'm going to start us off with a story. I imagine it's the type of story that you will all have loved to hear as kids because it's all about optimizing video games, and I know kids love optimizing video games. In this story, we've got a game developer. I'm going to call him Pete, which is partly because I think it's a good name, but might also be because I've got no imagination. You can make your mind up. Pete gets a job working at a new studio. He meets his new colleagues. They're all great people. He's super excited. The game that they're working on is something he's really enthusiastic about. He goes into the studio, starts his work environment up, gets a build of the game, and looks at it and thinks, oh, there's something wrong here. I must have built a debug version. I must have done something wrong because this is running really badly. And he goes to his boss and just sort of says, what have I done wrong? And the boss says, well, we've got some problems, but we're not totally sure what we should do about it. And Pete says to his boss, it's OK. I'll have a look and see if there's anything that I can help you with. So he gets started, and let's follow him on his journey. Let's see where he goes. So first things first, where's he going to start? I would always advise that you start with knowing what your budget is. What's your target frame rate? There are a few questions around this which will affect that, like knowing what your minimum spec device is that you want to run on, knowing which platforms you want to run on, and possibly you might have different target frame rates on different platforms. In this case, I'm going to keep things simple for the story. I'm going to say the team are aiming at 30 FPS on everything because it makes for some easy numbers, but they'll work with anything. You're targeting 60 or 72, just plug in your numbers. You can work everything out. So we take 30 little blocks in our 1 second. I did spend some time here, which might mean I've got OCD, double-checking that there are 30 of these. I'm fully expecting to find out when this goes up on YouTube or something that there aren't and I've messed up. We'll see. Typically, though, when you're looking at things in a profiling tool, you're not looking at the number of frames per second. You're actually looking at a length of time because that's what the tool is measuring. So rather than taking the 30 frames a second, we're going to take that. We've got 1,000 milliseconds, and we'll divide it by the 30 to give us 33 milliseconds for our frame. And if you're 60, you divide by 60, so on. Now, this team are also planning to ship their game on mobile devices. And on mobile devices, we typically advise that you leave some headroom. Things like thermal throttling can be an issue, especially on lower spec devices. So it's a good idea to leave about 35% or a third of your frame time as idle time to keep the device running nicely and cool. So I've just multiplied that in here. That gives us around 21, 22 milliseconds for a frame in our example. What does a frame in a game actually look like when you look at it in a profiler? So Pete sits down with one of the team members, Sam, another engineer, and says, where's your bottleneck in your game? Are you CPU bound? Are you GPU bound? And Sam says, I'm honestly not sure. I don't know exactly what those terms mean. And so Pete says, OK, I'll draw you a diagram. Pulls out a bit of paper or whiteboard, whatever. And you might have seen some diagrams that look a bit like this elsewhere, but we'll go through some of them here. Loosely, in a profiler, your frame is going to look a little like this. So you've got your 33 milliseconds of time. Your CPU is going to do some work over that. It'll be split roughly between some engine code, some of your code, and rendering code. These often might be a little mixed up, but generally the rendering code tends to be at the end of the frame. You simulate all your stuff for your gameplay, and then you draw it. The GPU will be the thing that's actually doing the drawing. So this rendering code section here is actually going to pass some work off to the GPU to do that. And if you've opened the Unity profiler or another profiler before, this might start to look a bit more familiar now. We've got frames either side of the current frame that we're working with. And you'll notice that while the next frame on the right there is starting to do work on the CPU, the GPU is still drawing the last frame. So there's overlap between the two of those. What will happen in this case if the CPU is taking longer than the GPU? I think I've got that the right way around. Let's go to the next slide. I have. If the CPU takes 40 milliseconds and the GPU is only taking 20 milliseconds, then the GPU is not going to be occupied for 20, so that's going to be waiting. And the key thing here is, if you speed up the GPU when your profile looks like this, it's not going to run any faster, because the thing that's holding you up is the CPU. If you've got things the other way around, alternatively, your GPU takes longer, but this time your CPU is waiting. And because the CPU has to wait for the GPU to be free to pass it the data for the next frame you're going to draw, its wait is often somewhere in there before or around the rendering code. This does vary a bit depending on platform, but you'll often see wait markers somewhere on the CPU side if this is what's happening. And here, the key thing we need to do is to optimize the GPU. If we were to do the CPU, we won't get any faster, we'll just wait for longer. Okay, says Sam, I think I've got that now. I think I understand what's going on. And Pete grabs a phone to test a build. He fires up Unity, hits his build button, waits for it to go to his device. I would generally advise that you try and measure stuff on your target hardware as soon as you possibly can. I know it's difficult, it's not always possible, but if you want to really understand what it's going to do on a low-end mobile device, test on a low-end mobile device. Now, I've got some profiles we're going to have a look at. I might not have the same awesome project that Pete and his team had. I've got some other project that I've been working with, but the steps should all work the same. And getting back to where we were in the story, Pete was asking about whether we're CPU bound or GPU bound. And work out which one of these is, you need to go through your frames in the profiler and look at each one to see whether the GPU or the CPU is the part that's taking the time. And that can be quite time-consuming to do in a capture. So let's come over to my laptop. Here we go, a profile that I've made earlier. And in Unity 6, we've added a handy new view to the profiler, which will show at a glance whether you're CPU bound or GPU bound. And it's this highlights module we have up the top here. So we can click in that, and it shows us down here for the currently selected frame, how much time has been spent on the GPU of that frame, how much time has been spent on the CPU. And the highlights bars up here, admittedly mostly yellow right now for this one, are showing whether we're GPU bound or CPU bound. You can set your target frame rate in here. So we can pick 30, or if we want to, we can set a custom value. So the team could come in here and work out the value that would fit their 20 milliseconds and then do that. So we'll come in here, we'll set our target frames per second. We'll go for about 50, shall we? That's roughly 20 milliseconds. And we see here that we're mostly GPU bound in this capture. Okay. We're GPU bound then, says Pete. We've got a capture, we've seen we're GPU bound. How are we going to speed that up, says Sam. I don't know. We'll come back to our slides a moment and flip over. What will we do if we're over budget on the GPU? There are a lot of different possibilities that you can use in terms of tools here. Typically, the best tools to give you timings for graphic stuff are those that work with the hardware that you're on. But there are things from like RenderDoc, ARM, Xcode, all sorts of things have their own ways of measuring things here. You can also use the frame debugger in Unity. That doesn't have timing information, so it's more about trying to understand the structure of your frame and what's going on in it. Can still be useful, because often the best optimizations are the ones where you're able to stop doing something you don't need to, so maybe you can find something in there. Pete explained some of this to Sam, and Sam still looks a bit puzzled and says, well, I'm still not sure what I should do here. I don't understand graphics stuff. I'm not a graphics programmer. We don't have a graphics expert here at the moment. What do I do here? And Pete says, well, I've got an idea. We can try this. And he starts drawing something. So there are a lot of different systems in game engines, and it's unlikely that any one of us is going to know how every one of them works, or even if you're a specialist in one system, you can often not know every detail about that system. So sometimes it can be difficult to understand why it might be running slowly. I like to treat them as a black box, but in this case, my slides are black, and that would look a bit boring, so I've gone with a red box. In my red box, I'm going to think about the inputs to the system and the outputs from the system. Every system typically has some things that go into it, and they'll produce something as the output. Using an example here, if we've got a physics system, that's going to take some things that go into it. It'll take a bunch of collision meshes. It'll take all your components, rigid body components and things like that. You'll make API calls into the physics system, and those things all combine to produce some output at the physics behavior. So when I'm thinking about something and I don't know exactly what's going on in there, one of the main optimization questions I will often ask is, what can I try and change? And it's not necessarily that I think we're going to leave it like that, but I can understand better why the performance is like it is. So looking at another system, if you're using UGUI or UI Toolkit here for UI, you think about the things that you can change for your UI setup. You'll have maybe some canvases, or you'll have some layouts on screen. How many of those do you have? Are the items in them static? Are they animated? What's changing about those that I can change? Can I change, the depth of things in the hierarchy or the layout? And just try experimenting with some of those things to see what that will do to my performance. So if, for example, we go back to the physics system and say, I switch all my collision meshes for spheres because they're simple to check, and that speeds up my performance for the physics system a lot, I've got an idea that maybe I need to look at simplifying some of my collision setup. So thinking about systems in terms of inputs can really help. Back to our problem, though, and the GPU. I've got a few common issues that we know that people hit on the GPU, and we'll go through some of those, but maybe it's worth thinking about this is how those fit with that as like a black box. So common things that we see, we often have things where we have expensive effects or shaders in a scene. We often have issues with overdraw, things like if you've got lots of UI and it's transparent, or more commonly particle effects and they're big and they're in front of the player's face or whatever. Those can cause GPU problems. If you've got super dense meshes so that the triangles are around the size of pixels or whatever, that starts to cause performance problems as well. If you have textures that are very large, then you've got to send those over to the GPU to draw them or move them around in order to use them or query them. And if you're running at high resolution, that can cause problems too. Now, there's a few of these that then there are obvious ways you can try and adjust those things to see if they're your problem and try using those to fix them. So here you might be able to change some shader logic to reduce the cost of a shader. You might be able to reduce the amount of overdraw. If you make some design decisions, you might be able to say, well, we don't need that much UI like that. We can lay it out like this. Or if your particle effects could be made a little more opaque and a little less transparent, have fewer actual particles in, that can help sometimes as well. Dense mesh geometry, I guess the relatively obvious thing here, just try simplifying your mesh geometry and see if that helps. There are ways with these you'll be able to see, when you get to know them, see them in the tools that I've mentioned earlier as well. Oversized textures, you can obviously reduce the size of textures. You can do that per build platform and things in Unity and set that up so that a low-end device might have a different set of textures that end up getting used. You can also turn on bitmap streaming for this as well, if you're using that, if it's 3D, and that'll reduce the amount of texture bandwidth you need. You can change the setup of your game to run at a lower resolution and upscale it. And this is something that, if you were paying attention during the keynote, you will have seen mention of the STP, and you can turn that on in Unity 6. You can use that to do your upscaling. We also have support for upscaling in earlier versions as well. So I've got a quick side note here. This is a mention of the adaptive performance package in Unity. And this is a good way to adjust your performance settings based on different devices. It has the ability to look at temperatures on mobile devices, and then you can adjust settings of different parts of your game based on that. So you could reduce the number of particles or particle systems or game objects, whatever it is that you can adjust in your game on a low-end device to try and make it run better. Yes, QR code there if you're interested in checking that out. Back to my story, though. We're not going to dig super deep into all that GPU stuff. That's enough for now. Pete and Sam find something, and they decide this is going to fix our problems. They tweak it a bit. Everything looks a bit better on the GPU side. They go back, and they take a new capture. And Sam notices something that he wasn't expecting. So this time, the frame diagram we saw earlier is a little bit simplified. What actually happens normally in Unity is the rendering code on the main thread up the top passes work off to the render thread. That, in turn, passes things to the GPU. And sometimes you can end up in a situation where the render thread actually takes longer to run than either the work on the GPU is taking or the work on the CPU is taking, and you can be bound by your render thread. Not generally common, but I thought it's worth mentioning here. The thing you're looking for normally is where it is that is most expensive, and that's what you're going to try and optimize. If you're using Unity 6, like this team is, you can go in and you can turn on the GPU resident drawer. And the GPU resident drawer will attempt to move a bunch of the render thread and rendering work to the GPU. So if you're bound by rendering cost on CPU, that's something that's worth trying. My understanding is that it worked particularly well if you've got a lot of stuff in your world. The GPU is super fast at knocking a lot of things out of through the system. So that's where it works best. So in this case, the team turn it on. They go back, fire up the profiler again, and now we're going to be main thread bound, I think. So what happens next? Well, we are going to go back to the profiler. Here we go. Nope. Try again. Here we are. And I'm going to load up my second capture that I made earlier. So we're going to have a look at this capture. We can see quickly from the highlights module that we are over our 20-ish millisecond budget all the time. And the thing I would normally start doing at this point in the profiler is to pick a frame that looks relatively expensive and just start having a look at what's inside it. So we'll pick one at random over here and select it and zoom out. So I guess the main thing I would advise when looking at things immediately in here is focus on the things that look biggest, because that's where you've got most to gain when you're optimizing. There are a couple of things I would check. I would make sure that you're profiling not in the editor. There are exceptions to that I might get to later if I've got time. And I would make sure that deep profile is turned off. The reason for that is that Unity Profiler is an instrumented profiler. So what deep profile does is to automatically add markers into all the C# functions you have. And this means, the instrumentation means, that every function you go into will have a little bit of cost to measure it and a little bit of cost at the end as you come back out of it. And it makes deep call stacks look more expensive than they really are. So you'll often see a deeper call stack will start to sort of spread out and look bad. What deep profile is useful for is the case where you've got a big gap in your profile and you don't know what's going on. Like maybe I've got a little gap on the end. If you've got a big gap, turn deep profile on and see what's in the gap. If there's some C# code running, that'll tell you. You can turn it off and continue. You can use the profile markers, that point, profile marker begin and profile marker end yourself, and the code will start to appear when you've added that marker. Okay. We've picked out a frame to investigate here, and Pete spots the function down here, player target setup, and has a little bit of a look around and notices that we're seeing that in all of our frames and thinks that's a bit strange. It says setup, and I'm seeing it every time. So goes to have a look in the code and sees it's something that is supposed to be set up once when the player spawns in, and it's got a bool, but nobody's ever setting the bool to true, so it's doing it every time, and quickly just fixes that one up. And then we notice down here, we have a lot of markers for GC alloc and GC collect. and dig into exactly what we're going to with that. And those suggest that we're allocating lots of managed memory this frame, and then the system is having to go away and free it. If you're seeing lots of GC alloc calls, but not lots of GC collect calls, you're allocating quite a lot of memory. But if like this, you see lots of collect calls, you're allocating a lot of memory. And you can then come into the hierarchy view here, and bearing in mind this is a sample I've knocked up to show you, we're allocating 200 megabytes of memory a frame in managed memory, so that should be pretty easy to find. Sure enough, Sam digs in, goes and has a poke around the code, quickly sees what the problem is, and gets it fixed. So, back to my slides again. There we go. At this point, Pete and Sam stopped for lunch. That's a good morning's work, right? Fixed all those performance issues. What do you think we can get done in the afternoon? And he goes and sees his boss and says, I think things are looking a bit better. I understand where some of the time's going, and the boss looks relieved. So that's all good. And then I think, at this point, we could just say the game's running fine and leave them to their happy lives. But for the purposes of our story, I'm going to drop them into more trouble and give them another performance problem that they need to look at. So after a while, the team are going to prepare to show their game at a show. They get things up and ready, but Sam notices that the game has started glitching a lot when people are playing. And Pete's busy with something else, so Sam's like, I know what I'm doing with the profiler now. I'll start it up, I'll have a look. And goes back to look at the profiler. And we will join him. Got spikes. So we have some spikes in our capture. And this is what we'd expect to see when we've got problems where the game is glitching. It's running smoothly, suddenly glitches. These spikes here are those glitches. Now, we will switch to using Profile Analyzer here. Now, I actually have an info slide I should show you first about Profile Analyzer, just because I have a QR code. It's a package, and you'll need to add it into your project. So if you're interested, this should link you to the getting started instructions and documentation. That should show you where the package is, how to find it. Profile Analyzer is a tool that takes data from your existing profiler captures and then gives you more detailed information about what's going on in that frame. So we will switch back and have another look at it. Here we go. So we have data in the profiler here. In Profile Analyzer, we can click this button up here, Pull Data, in the corner, and that will load the data from the profiler capture in here. I've already done it to save us messing around. But then we see the same capture in this graph up the top here. And we can do things. Everything is selected at the moment, but you can select the shortest frame in there, the longest frame in there, and analyze those specifically. You can look over here at our frame summary, and this shows us how many frames we've got. But it also tells us what the most expensive frame in our capture is. In this case, you can see pretty easily, but if you've got a more complicated capture and you're interested, it tells us loosely how long the upper quartile, median, and lower quartile frames are taking. So if you're interested in those numbers, they are here. And you get a nice little graph showing you exactly what the distribution is. So these are the fastest frames and these are the slowest frames down here. If we were to click on one of these and select it, then that jumps to that frame in the profiler, so you can go back and look at that frame's timeline view or hierarchy view and pull out exactly what you'd see on that one frame. Down here, we see a list of the markers for a frame. What we're going to do, I'm going to narrow us down to one of these spike frames by clicking on it. And then in this view at the bottom here, we can see a list of the markers in that frame and what's most expensive. Now, it's not surprising to see things like player loop at the top because everything is in that. But this marker down here, where we see the drop between the longer markers and the shorter ones, is looking a little bit suspicious. And in case you can't read it, in this case, it's Pathfinding Manager Rebuild. So there is some code in the game doing some pathfinding, and that's what's caused this spike. Once we've selected it over here, we can look at it down here in the marker summary. I'll fold up the frame summary so we can see more of this. You can look at things like the top frames by cost for this marker. If I select all our frames, we've got the same marker selected, but now we can see the top 10 frames in our capture that are using this. Interestingly, there are, 6 of them here, and there are 6 spikes. So I suspect this is what's causing all of those spikes. You can actually go through and look at them, see frame 292, yes, that's the top one, and so on. Double check that. And we can see that's what's running in all our spiky frames. So at this point, Sam thinks, okay, this is super suspicious. I'm going to go away and fix this. I'll come back. We'll see where we get to next. Sam captures a second profile. And here's another thing you can do in Profile Analyzer, which is to use compare. So you can look at 2 different captures at the same time and see what the difference between those captures is. At this point, I'm going to just load in my existing data here. You might notice it's called Spikes Gone, a bit of a spoiler for what's coming next. That one, I'm not convinced that's the right thing I've got there. My apologies. Just load it in here and pull the data. There we go. Okay, so now at the bottom here, we have a comparison of those 2 captures, and you can see what the difference between the markers is. In this case, the capture that we've just loaded with the spikes gone is actually showing up as being a little bit more expensive, but you can see in the table here that we've got some markers that are occurring more times in that capture. So I'm not too concerned about the fact that the numbers don't match up. What I'm most interested in is being able to search in here and say Path Finding Manager, rebuild, and I can see from the blue bars here that it's completely gone from the second profiler. The blue means it's in the first capture, and it would be an orangey color if it were in the second. Can demonstrate that with another marker that's in both of them. So it's completely gone, and Sam has fixed those spikes. I guess the thing that I would advise here really is measure before you do something based on what you've measured, and then measure again afterwards and compare it and check that you've actually fixed the thing you think you've fixed, because it can be easy to expect something to fix a problem and then find that it doesn't, or that you've had some other knock-on somewhere else and caused a different problem. There is another feature I'm going to mention while we're passing. Up here we have an export button, and you can export data from Profile Analyzer as CSV. We often get people asking how they can get the profiler data out of the profiler. We do have an API you can use for the profiler to get some of that information out, but if you just want a quick export, this is probably the easiest way to do that. Load things into Profile Analyzer, click export, and take the data from there. Okay. Story continues. The team releases their game. Everybody is happy. They all live happily ever after, except we know I've still got a little bit of time left, so they don't. We have more performance problems. The game goes out in the wild. Users start playing it on their low-end mobile devices, and they're running out of memory and crashing. What should the team do here? Well, again, I would say know your budget. If you know what memory you've got available on your device before you start, you can try and avoid this problem to begin with. But in this case, the team didn't, and now they're here. They know which device it is that's crashing. It's a device that's got 2 gigabytes of memory. Okay, this is going to be a problem. 2 gigabytes should be their budget, shouldn't it? No, it's not. On mobile devices in particular, but on most devices, you can't use all of the memory that you've got in there. And on mobile devices, it might be lower by 50%. So typically around 1 gigabyte on a 2 gigabyte phone's a reasonable place to start. You might need to go a bit either way, depending on exactly what you're looking at. This is also one place, like I've mentioned earlier on about profiling on target devices, but this is somewhere where you need to be careful about that. I mean, careful, but you don't need to do that here. You can profile on a bigger device, see how much memory you're taking, and then you'll know how much over your budget you are. So I would actually advise when you're looking at memory, just profile on something big, similar setup so that you've not got different settings and different assets, but then do your working out what you're going to work on from there. With this budget of 1 gigabyte, we can have a quick look in the memory profiler module in the profiler window, which will be down here. This doesn't have useful data in to look at here, but this is this is useful for getting a rough idea of what's going on, but it's not actually where I'd advise going once you know you've got a problem. You get some idea of what different categories things are in, but it's quite difficult in here to tell what was actually being used in the device's memory, whereas devices have resident memory, things that are in memory. They have things that are part of your process's memory space, but not actually currently in the memory. It's what's in there that counts when you're running out. I would advise using Memory Profiler as a starting point. And I am going to go back here because, once again, this is a package. And this will be a link to the documentation. If you're not sure where to get started, follow the QR code, add it into your project, build for your target device, start running your game, hit capture, and see what you find. So Pete and Sam get this package installed, they start it up, and we'll come back and have a look at what they see. So this is the main page that you'll see after you've got a capture in the Memory Profiler, the summary page. And this now has a section showing you total amount of memory resident on device. And this is the amount that you've actually got in device memory when the capture is taken. This thing here, I guess one thing that I would emphasize about this is something that we've made a big push on in Unity 6 to try and make sure it's actually as accurate as we can get it. So numbers from that should be useful enough to work out where it is that your resident memory is. Now, for memory problems, I've got some things that we can go through and have a look at and talk about like I did for the GPU. Typical things, I guess, again, I would advise looking at big stuff first because that's where you can make biggest wins. And looking at this on the summary page, you can see loosely where your resident memory is going. The categories is probably a good place to start because that gives you a view of where your actual memory is. This project apparently has an awful lot of render textures in it. Once you've been and look at things in here, you can then go and look for that particular category in Unity objects and drill down into where it is that you're actually, where your textures are, where your render textures are going. The managed heap utilization section here is another thing that I would take a look at. This is measuring what you've got in your managed memory, so your C# objects. And this just gives you a rough high-level view of where that is. But if we come across the Unity Objects tab here, we can see for all our objects, by sorting by managed size, where exactly it is that our memory is going in there. Typically, the things you're probably most interested in are going to be monobehavior and scriptable objects, but anything counts, right? So if you see something big in there, try investigating it and see where it goes. Duplicates. So we have an option in Memory Profiler that will attempt to figure out when you have duplicate things in memory. It's easy to accidentally load something twice if you have things in asset bundles or addressables. In addressables, you can end up, for example, having assets which get packed separately, but both depend on something, and they both have their own copy of the dependency, and with them, you end up with two of those loaded into memory, which you didn't want. This is a good way to look for those, highlight where those are. Now, I have, if we can get this to come back to my presentation, a handy QR code. In case you are interested in going and fixing duplicates in Unity, we have a blog post that walks through the process of doing that with addressables and links to other assets. So that's a good place to go and take a look. So at this point, Sam sees a couple of things he thinks they can fix, passes them on to somebody else on the team, keeps investigating where it is that memory is going. And come back over to the memory profiler here. So another thing that we've worked on in Unity 6, in graphics section here, we now have a breakdown of details about, for example, all the render textures that are being used. And you can actually see what size they are, how big they are in memory, and track that and work out where it is that your render texture memory is going. There are some tricks that you can try and use here. You can maybe share some render textures between things if you've got stuff where you're using them yourself and you happen to know exactly how they're being used in the pipeline. But another common thing is to reduce the size of some of them and just do things at a lower resolution. Another thing that it doesn't really fit into any of these tabs, but is a useful thing to bear in mind if you're doing memory optimization, is just thinking about asset use in your game and your game world. Maybe, for example, like the team here, we've got a boss battle in the level, and we don't need to have the assets for the boss loaded for the whole thing. So we could have the boss's mesh, sound effects, animations, all of these things packed separately and loaded separately. Asset bundles and addressables are good tools to look into for doing that sort of thing. In this case, maybe they've done that with the boss battle. The team decide they've got some cutscene assets that they can do that with as well and clear those up too. Now, another thing we can do in Memory Profiler is to have a look for leaks and compare memory use over time. And up here, we have a compare snapshots tool. I've already got this one loaded in this top slot, and I can click on this one here to load something in the second slot. And this will show us the memory being used at the start of the level, the memory being used in the middle of the level, or wherever you've taken your snapshots. Common use cases might be that you say take a snapshot on a front end, go into levels and take another snapshot after you come out of the front end and check to see where you're leaking memory if you are. In our case here, Sam has a look, heads over to the Unity Objects tab, and you can see a difference that shows exactly where that memory is going. We see a particular thing in here that's gotten bigger. Sam decides that's a problem and goes away to fix it. So things are looking good. And back again. Now, the end of the story. And this time we actually are coming to more or less the end of the story. I'm not going to drop the team in too many other performance problems. Team shipped the game. They've released it. They've fixed their memory issues. Everybody's happy. Their players are coming back. And they all live happily ever after. Except in the real world now, with live games, they'll probably actually end up wanting to look at performance for a long time on this project. Things that they might want to consider here are adding in performance tracking and measuring performance automatically as they work on the project so that they can not have to worry about it each time they do a release. Yeah, and you might have guessed here, but the end of the story means we're coming towards the end of the talk. So I'm going to wrap things up a little bit. I've got some kind of maybe best practices around profiling. First main thing, don't ignore performance problems if you've got them. You don't need to fix them, but try and understand them. Sometimes you might look at it and you go, this is fine, we'll get to this later. But don't ignore it. So going back through the things I've talked about here, know your target frame rate. If you don't know what you're aiming for, you're probably not going to hit it. So try and keep that in mind. I would suggest profiling often. Now, some people might say that's because I'm biased and I work on profiling tools. But in reality, I think it's good to be familiar with the tools you've got available. The more familiar you get with it, the easier it is to open it, look, see what's going on, and then get on with whatever else it is you're doing. And the other thing that's worth noting here, I don't say optimize often or anything. Just have a look in the profiler. When you add some new things in, check and see it's how you expect it. Aim to profile on your minimum spec device as soon as you can. Yeah, it's not always possible to start straight away at the beginning of your project, but if you can, do it. Now, this one's a bit of a strange thing, but make sure that when you're profiling things, you profile the game that players will actually play. I've seen studios do things where they work in test projects and test levels, which is fine. It can be really good for iteration time, but it's probably not the best place to do your profiling. If you can do that in the actual game levels, that's a better place to do that because it's what you're actually going to be shipping. Setting budgets for different systems is worth thinking about if you can do that for your project. I know most teams are long familiar with having some idea of what they're going to do in terms of like art budgets and things like that, but having an idea how much of your frame time you're expecting to spend on physics versus your custom game code is a useful thing to think about. It then also gives you something you can be measuring and checking. You can query with Profiler APIs, for example, and check that for your game. Setting up automated performance testing, I mentioned that just now as well. If you can set up something where your levels are run when you add commits into the game or something and just check a performance number, that's always a nice thing to have. It gives you a bit of peace of mind. You'll know that your game's going to run okay. Some more best practices. Optimization is time consuming. Make sure that you do have some time available for it. It's always difficult to fit in projects because everything overruns and slides towards the end. And that's normally when people end up having to do the optimization work because all your assets come into the project. But I mention it here. If your engineer and your boss is saying you're not going to have to point them at this, you need time to optimize properly. It's not something you can just squeeze and hope it'll fit in. Profile before and after optimizing, we've been through that already, but it's good practice to check that you've actually fixed the thing you think you fixed. Add profiler markers. Don't go using deep profile for things when you're actually profiling. It's not going to give you the same sort of accuracy in terms of your timings. Focus your optimization on expensive parts of your game because those are the bits where you're going to have, I mean, it's obvious when you're focusing it on the area you've got a problem, but if you focus it on the expensive part of the frame, that's where you've got most to gain as well. For memory profiler best practices, I only really have one. The others largely apply, but this one is don't worry about the minimum spec thing so much with the memory. You can profile on something bigger, you can fit it, make sure it fits. Okay,